My name's Scott Rodowitz. I'm currently a postdoc at Stanford's Graduate School of Business. I'm going to be talking about fair dynamic rationing, which is joint work with Vahida Manshade and Rodney Azada. I should say, first off, big thank you to the organizers and session chair and all the other presenters. It's really exciting to be a part of this first inaugural EAAMO conference. So I'm happy to be here, and thanks all of you for attending. So I'm going to start things off by introducing a general class of allocation problems before getting into a little bit how this relates to the topic of the session. So suppose you as a social planner have been tasked with allocating some desirable social good to agents who are going to arrive sequentially. When they arrive, you'll observe their need, and you're going to need to make an allocation decision at that time. Now, these needs might be arbitrarily correlated, so that you can have a pretty challenging scenario here. And let's think about what your goals might be. So suppose you want to be efficient. So you want to use as much of your supply as possible. Well, that's actually a pretty simple problem. You can just allocate on a first come, first served basis. You're going to use as much of your supply as you can. But the problem is that you might be very unfair to people who arrive later on in the process. You might run out of supply, and so whoever shows up last is probably not going to get it. Now, alternatively, let's say you want it to be very fair. You want to make sure everyone gets the same amount. Well, that's also pretty easy. Just don't give anyone everything. Don't give anyone anything. And in that case, everyone gets the same amount, but of course, that's a silly solution as well. So in this talk, what we're going to do is think about balancing those two extremes, how we can achieve dual goals of efficiency and equity, at least to the greatest extent possible, when thinking about a sequential allocation problem. So this is a common dilemma faced by nonprofits and governmental agencies. And to motivate that, we can take a step back in time about 1.5 years ago to the onset of the COVID-19 pandemic in the US. So here you can see states are going to have outbreaks that are going to occur at different times, or at least they're predicted to occur at different times. The size of their peak outbreak is expected, of course, to be of different sizes. And so the needs that these states are going to have are unknown in advance. But they're, of course, also correlated. If things are pretty bad in the Northeast, it's not like it's then going to be smooth sailing for other states. There's network effects in the pandemic. If it's bad somewhere, it's presumably going to get bad in other places. So if you put yourself in the shoes of the Federal Emergency Management Agency, which had control of this federal stockpile of emergency medical supplies, you can think about this scenario in the cartoonish introductory example that I showed you. So to be precise, you can think about observing the need that New Jersey has for, say, ICU beds in this first week of April. And you need to make an immediate decision about how much of that need you should meet, knowing that next week, Connecticut is going to have significant need, and probably the week after, Tennessee is also going to have significant need. Now, you may know to some extent what the expected value of that need might be, but there's a lot of variance around those projections. And of course, there's correlation as well in these scenarios. So it's a pretty challenging question to ask about how FEMA should ration supplies both efficiently and equitably. And I want to take a moment and say that there's plenty of other examples in social good settings where these types of questions arise. So you can think about hurricanes that sequentially impact municipalities and the rationing of emergency response resources. You can think about mobile food pantries that sequentially visit agencies. Again, you have the same type of question where need is going to realize sequentially, and you need to make allocation decisions in the face of potentially complex correlation. All right, so this is our motivation. I want to introduce our general framework for studying these types of problems, including our model. So we're going to suppose that we have just one unit of supply. So we're normalizing this. It's divisible. And we have a sequence of agents that arrive. And when they do, we observe their demand. Up front, we know the joint distribution of their demand, which can have any sort of arbitrary correlation. Now, when an agent arrives, we need to immediately and irrevocably decide upon the allocation to give that agent. And each agent is going to care about their fill rate being the fraction of their demand which is met. Now, this fill rate is going to be some number between 0 and 1. Agents don't need more than what they ask for. And to balance equity and efficiency, our goal is going to be to maximize the minimum fill rate. So I put this idea of a minimum fill rate in quotes because it's somewhat poorly defined for the stochastic process. There's a few different ways we can think about taking expectations, and those correspond to two different objectives, two different notions of fairness. The first is this ex post minimum fill rate, which is about fairness in observed outcomes. And the second is the ex ante minimum fill rate, which is about fairness in expected outcomes. So we're going to care about both of these objectives, and we'll have results for each of them. All right, so that's our framework. I'm going to jump right into our main result. So in the paper, we design an adaptive policy which simultaneously achieves the best possible ex post and ex ante minimum fill rate guarantees. So said another way, no sequential policy can guarantee a better ex post or ex ante minimum fill rate. So not only do we have strong theoretical guarantees with our policy, which I'll introduce to you in a moment, it's also practically appealing. So our policy is computationally efficient and transparent. It requires minimal informational knowledge about this joint distribution F, and it naturally generalizes to a few other considerations. And these qualities, I should say, are particularly important in public sector settings, right? Transparency is often a chief objective of these social planners, people who are making allocation decisions. All right, so before introducing our policy, I'm going to start by considering a simpler setting, and that'll give us some intuition behind what is achievable as well as what our policy does. So suppose for a moment that we knew the entire demand sequence in advance. Suppose there was no stochasticity in demand. What would you do? I'll let you think about it for just a few seconds. All right, so if you thought about something like proportional allocation, you did a great job. What we want to do is equalize the fill rate for each agent, and then we want to raise that equal level as high as we can. And this is for both the ex post and the ex ante minimum fill rate. Now, if we do that, we get a minimum fill rate of either 1 or 1 over the total demand, whichever is smaller. And so that's what's achievable if demand was deterministic. Now we're going to use this in our notion of a fairness guarantee. So to be precise, we're going to fix two parameters. We're going to fix mu, which is this expected total demand, right? Our supply is normalized to 1, so this can also be thought of as the demand to supply ratio in expectation. And we're going to fix the number of agents n. This is the number of decisions we need to make. And then we're going to say that a policy achieves an ex post fairness guarantee of kappa mu n if for any demand sequence with an expected total demand of mu and n agents, we can achieve a kappa fraction of what we would hope to achieve, or of what we could achieve if demand were deterministic. So this is saying, what's the cost of having this stochastic demand sequence? And we're going to try to design policies that have good guarantees on their ex post minimum fill rate and their ex ante minimum fill rate. So for the remainder of this talk, I'm going to focus on this notion of ex post fairness. We do have analogous results for ex ante fairness. The ex post results are pretty emblematic of what we can say in the other case. All right, so I'll start with the bad news. So unfortunately, no sequential allocation policy can achieve an ex post fairness guarantee better than this surface for kappa. It's decreasing in the number of agents, as you might expect. The more decisions you have to make, the more challenging this problem becomes. And so we're not going to do any better than this parameterized surface. But in fact, we can achieve exactly this upper bound, and we can do so using a fairly simple adaptive policy. And that policy is called projected proportional allocation. It's based on the optimal policy if demand were deterministic. And so the way I want you to think about it is, well, what would you do if you knew what demand was going to be? You'd allocate proportionally, as we discussed. So because you don't know future demand, you can't do exactly that, but we'll do the next best thing, and we'll replace future demand with its expectation. So to be precise, we're going to take our first observed demand, we'll take our full initial supply of 1, and we'll allocate to this first agent proportionally to what we expect total demand to be in this 3-agent scenario. Then we'll observe the second demand. We'll take our remaining supply and we'll allocate that proportionally, again, based on what we expect demand to be. Note that we're updating demand here based on every observation we've made so far. All right, so in the paper, we're able to show that this projected proportional allocation policy achieves exactly that ex post fairness guarantee of kappa that I showed you earlier. And we're able to show this by inductively establishing a lower bound on the value to go of our policy for any particular state. So I'm not going to get into the details here. Instead, I'm just going to highlight that this policy, as I've mentioned, is simple. It's transparent. It's pretty clear what's going on. It's easy to communicate to stakeholders. And it also requires fairly minimal distributional knowledge about this joint distribution. All we need to know are conditional first moments of each agent's demand. All right, so like I said, we have analogous results for ex-ante fairness that I'm not going to get into today. Instead, I'm going to talk about these other properties. So our adaptive policy has these nice properties, but it's natural to wonder whether there's a simple non-adaptive policy that could do as well as what we achieve, and of course also have some nice properties for application in this public sector context. So to shed some light on this question, we considered a class of non-adaptive policies called target fill rate policies, which work by predetermining a threshold tau and then aiming for a fill rate of tau until supply runs out or until all of the agents have arrived. So you can think about optimizing over tau, in which case you get what we call the optimal target fill rate policy. And in the paper, we're able to exactly characterize the performance of this optimal TFR policy. So in all cases, it's strictly below the performance guarantee of our PPA policy. In some cases, it asymptotically approaches this guarantee. That occurs when there's a large number of agents and supply is quite scarce. In other cases, if there's not too many agents and supply is well matched to expected demand, there's a significant gap in the guarantee of our PPA policy and the guarantee of the optimal target fill rate policy. Now we're able to show this result via a connection to a constrained version of a single item monopoly pricing problem, which is a somewhat interesting technical result. I'd be happy to talk about it offline in the interest of time. Not going to get into the details here. Instead, I'm just going to offer a brief comparison between our policy and this optimal TFR policy. So both are pretty simple and fairly clear in terms of what they're accomplishing and how easy they are to explain. In their own ways, both require minimal distributional knowledge as well, right? We just need these first conditional moments for each agent's individual demand, whereas the optimal TFR policy requires full knowledge of the demand, but only the total demand distribution. All right. So with this all in mind, I want to take us back to this motivating case study of COVID-19, back to the topic of this session. And so we've built a case study using a demand model that was in place and was studied by the White House in April 2020. So we looked at projected need for ICU beds as a proxy for just overall demand for medical supplies. We partitioned states into 4 groups to make this setting pretty simple. Now, this demand model that we're using from the IHME doesn't have a full distribution. It just gave a few percentiles. So we put a normal distribution on top of this, and then we assumed various levels of correlation between these 4 groups. And we looked at results for 4 different levels of correlation. So there's a few different things I want to highlight for you here. First, our PPA policy significantly outperforms its theoretical guarantee. It also significantly outperforms an optimal TFR policy, especially in the presence of correlation, which should make sense. Our adaptive policy is going to have a big advantage in those types of settings. And it even compares reasonably well to a dynamic programming solution. So, right, this is a well-defined optimization problem. You can formulate a dynamic program. In many cases, that DP is going to be intractable. We made this fairly simple so that we could solve the DP. And even despite this, our policy is almost as fair as a dynamic programming solution. And of course, it's much simpler. It's much more transparent. It's not this black box. and you don't need full distributional information. So we think there's a lot of good reasons to use this pretty straightforward policy in practical settings. All right, so to sum up, I'm running out of time. What have we done? We looked at how to achieve dual goals of equity and efficiency when facing an arbitrarily correlated sequence of demand. And we've showed that all you need is a simple and transparent policy called projected proportional allocation. I encourage you to check out the paper with proof ideas as well as some extensions for this work. And thank you very much for your time, your interest, and your contributions to making this conference as exciting and fun as it is.
Well, something that I'm curious about here is, I mean, I think it's a really interesting property that the allocation rule that you propose requires such minimal distributional information. But even I think these conditional first moments, can be pretty difficult, right? Like, epidemic forecasting is really hard, right? And models have often been, pretty bad at predicting when exactly searches will happen. So how much robustness do you think there is to sort of, misestimation of those? Yeah,
that's a really good question. I think I'm going to defer giving you a full answer. It's something that we're working on right now, actually, to add to the paper. I would say that if there's model misspecification, it can definitely cause some problems. I would argue that it's going to cause generally less problems for this type of solution than a dynamic program, which is going to be very reliant on accurate demand distributional information.